In 1973, the largest ever peacetime explosion to date in the UK occurred at a chemical plant in Flixborough, a record that would be held for 32 years. NYPRO UK was a joint venture between Dutch State Mines and the British National Coal Board. It was close to the towns of Flixborough and Burton upon Stafford on the banks of the River Trent in North Lincolnshire. The site occupied approximately 60 acres of land and initially produced fertilizer using the byproducts of coke ovens at a nearby steelworks. In 1967, as the price of fertilizer went down and the price of nylon went up, it started manufacturing caprolactam. Caprolactam is a key ingredient in the production of nylon and is produced from cyclohexane. To begin with, caprolactam was produced from the hydrogenation of phenol, but as additional capacity was added in 1972, hot liquid cyclohexane was partially oxidized with compressed air to produce cyclohexane-1, which was then used to produce caprolactam. To produce cyclohexane-1, the liquid hexane would be heated to a temperature of 155 degrees centigrade with a pressure of 125 psi. It would then pass through 6 reactors, each with its own feed of compressed air, and each at a lower elevation than that of its predecessor to enable the use of gravity to control the flow of cyclohexane. Approximately only 6% was reacted, and so the unreacted cyclohexane would be sent back to the start of the reactor loop. On Saturday, the 1st of June, at approximately 4:53 p.m, a huge explosion occurred at the Flixborough plant. Approximately 30 to 50 tons of cyclohexane had leaked from the process, ignited, and explode with roughly the same force as 15 tons of TNT. On the site, there were 28 fatalities and 36 injuries. These numbers would have been a lot higher had the explosion occurred on a weekday. Off-site, there were around 50 injuries and over 2,000 properties damaged. I was watching TV at the back of the house with my brothers when I heard a massive noise that felt like it went right through me. We all went to the front of the house and all the windows had been blown in. I remember being really worried about my mum and brother because they were out shopping at the time. Liz was 10 years old at the time of the explosion. She was at home watching football with her fathers and brothers. After the explosion, I had to help with evacuating families to Gainsborough and reuniting families that had been displaced. It was like a war zone. The village had been completely flattened. Peter was a vicar at Flixborough at the time and acted as a go-between between the residents of Flixborough, the local council and the representatives from NYPRO UK. He arranged the funerals for many of the fatalities. So, what actually happened? On March 27th, a crack was found in Reactor 5 and the plant was shut down for investigation. A bypass pipeline was installed and the plant was reopened 5 days later. By the end of May, more cracks were found across the process and the plant closed down again. An attempt to restart the plant was made on the morning of June 1st. Further leaks were found and fixed, and the heating of the cyclohexane stream began. Just after 4:50 p.m, the temporary pipeline deformed in a V-shape due to the bending stress, and the bellows were torn away as a result of shear stress. A vapor cloud of cyclohexane escaped, and at 4:53 it ignited, causing the massive explosion. At the end of March 1974, a large crack was found in Reactor 5, and the plant closed down while an investigation was undertaken. The plant fixated on returning to operating as soon as possible without regard for whether their suggestions and actions were safe and suitable for the process. Reactor 5 was deemed to be unusable and so was removed. Without a works engineer to approve these decisions or make judgments on the safety, a makeshift pipeline was put in place to allow the flow between reactors 4 and 6, and production quickly continued. A dog-legged pipeline was used to accommodate the height difference between reactors 4 and 6. They used a 20-inch diameter pipeline as this was the only available size that was on site at the time, and production needed to begin as soon as possible. It was worth noting that the original lines connecting the reactors had a diameter of 28 inches. The original lines also did not have a dogleg in them, something that wasn't accounted for in the little calculations that were done, a dogleg in a high-pressure pipeline does have a large effect on the process. The difference in the size and shape of the pipeline was not accounted for as the overall process conditions did not change. Very few calculations were actually made during the installation of the pipeline. The effect of a pressure rise on the pipe was not considered. The pressure rise was the result of the new shape and significant decrease in pipe diameter. In industry, the difference in the conditions that a half-inch change in diameter can make is significant, let alone an 8-inch difference. In addition, mechanical calculations regarding the pipe shape or bellow integrity were not undertaken. The bellows seal valves were not built to handle the conditions that the process operated at. In addition, the plant decided that to take the weight off the bellows, simple scaffolding could be used to support the new pipeline. There was no other support mechanisms in place. A full assessment of potential consequences of the bypass installation was not also considered. The relevant British standards were not consulted, and the design guide for bellows was also not referenced. So, what was the cause of the accident? The makeshift bypass ruptured and leaked a large quantity of cyclohexane. The cyclohexane vapor then ignited and exploded. It is believed the source of ignition was from a furnace some distance away on another part of the site. And what was the underlying cause of the rupture? The official report claims that the bypass failed due to an unanticipated stress during a pressure surge. However, this has been argued against by many people over the years since, and there are now two main theories about what caused the Flixborough disaster: the 8-inch theory and the 20-inch theory. The initial investigation found that a split had formed in an 8-inch pipe near the cyclohexane leak. This was due to a leak caused by two loose bolts at a flange on a non-return valve. A build-up of oxidizable residue was then ignited by an electrostatic charge, which in turn caused a small flame in the pipe. Some believed that this caused a small explosion that caused the failure to the bypass, and the secondary, much larger explosion. This was the position the NYPRO UK and its insurers took up. This was supported by eyewitness accounts, but the court brushed it off, saying eyewitnesses can be confused about what they saw. After the explosion, the bypass assembly was replicated in an attempt to find the cause of the explosion, and it was determined that the 20-inch dogleg pipe was the most likely source of the leak. It is believed that unbalanced forces on the bends in the pipeline, coupled with the flexibility from the expansion of the bellows, allowed the unsupported jumper to oscillate, causing the crack. Initial tests found this wouldn't result in leaks before the safety valve was triggered. However, theoretical modelling showed that the conditions the plant operated under, especially during startup, could lead to tears below the safety valve setting. When thinking about the cause of the Flixborough incident, it is worth considering the following things. After the works engineer had left the company, prior to the removal of Reactor 5, a replacement still had not been found. NYPRO UK offered up a works engineer, however, they were never called for, or present during the initial meeting after Reactor 5 had a large tear. After Reactor 5 was removed, no checks were done elsewhere in the process to check for damage. There was financial pressure on the plant to resume production as soon as possible. This, along with the additional workload on employees due to vacancies, could have led to staff being distracted and potential consequences being overlooked as a result. Health and safety at Flixborough. Was it done right or just to the law? The control room was where the majority of the deaths occurred. Out of the 28 people who died at Flixborough, 18 were from the control room. The control room was located close to the process, and therefore the reactors. The blast caused the roof of the control room to collapse, thereby trapping and killing everyone inside. No one made it out of the control room. The initial investigation found the control room was not built to withstand a blast, and subsequent research has told us that occupied buildings should not be placed near the process. However, the control room was not an outlier in not being the way it should. It was comparable to its contemporaries. It was just the unlucky one. The next problem comes with the bypass pipeline, which is believed to be the main source of the explosion. Initial reports said it was due to a mechanical error. However, later investigations found there was an intentional cover-up of the incompetency at Flixborough. This was shown by no proper calculations being made prior to the installation or afterwards. This includes no pressure calculations for a high-pressure process. These calculations would have been especially important due to the uncommon dog-legged pipe, which would have caused the issues. There were no proper diagrams drawn for the removal of Reactor 5 in a new bypass pipeline. Instead, they decided a chalk diagram on the floor would suffice. Obviously, this did not go well, and increased pressure led to the rupture of a pipe which leaks the cyclohexane. The plant did not account for the fact that such a disaster could happen instantaneously. This allowed for poor workmanship and the use of materials that shouldn't have been used. There was also no mechanical engineer on site since before the Reactor 5 ruptured in March 1974. They had no one who could do the proper calculations and fought to allow an unqualified person to do the work to prepare for the bypass pipeline. Most of the plant management were chemical engineers and overlooked a mistake in the mechanical design of the system. Today, chemical engineers are taught mechanical design of pipes and vessels. However, at the time, chemical engineering programs were not interdisciplinary. As a result of these factors, a major explosion occurred, killing 28 people and seriously injuring 36 others on a plant that had 72 workers that day. Did Flixborough legally do anything wrong at the time? No, they didn't, and that's the unfortunate part. There was no health and safety executive at the time, which today would have been responsible for making sure the chemical plants are safe and that proper calculations have been made to each change made, even if it's to fix a reactor. The Health and Safety at Work Act had yet to be put into law. It was the explosion at Flixborough that pushed it to be drafted. This act holds employers responsible for keeping their workplaces safe for employees. This helps prevent disasters today. However, at the time, there is no inspections regularly taking place, something that could have caught a disaster beforehand and prevented an incident. There were no regulations from governments to the standards that parts of a chemical plant have to follow. These would come later in the decade as a result of this disaster and the Seveso disaster. However, at the time, there was no accountability for these plants to do the correct thing. What was done was incompetent, but there was no structure in place to counteract incompetency. It took a major loss of life for governments to realise that there is a need to keep an eye on chemical plants. Despite the fact that the blast at Flixborough killed 28 people, it was lucky to have not killed more. The blast occurred on a weekend. Subsequent investigations found that if it had have been on a weekday, there would have been many more casualties. What causes financial loss in an accident? Many factors are considered when looking at the overarching financial cost of an accident as severe as that of the NYPRO plant in Flixborough. Some examples of such costs are the impact on people in terms of fatalities and injuries, the property damage, whether that be company owned or those in the surrounding area, as well as repairing or replacing damaged equipment, business interruptions such as lost production. This can cause additional issues if this stops a major revenue stream when you are still subject to the fixed costs of your plant, such as loans. The cost of lost inventory, again from sources and other damaged equipment. Environmental damage, including cleanup costs and the impact on local animal and plant life. Plus, any other outcomes with financial impact, including legal costs, fines, loss of reputation, brand damage, compensation, and reduction of share prices, and so on. The cost of Flixborough. Estimations of the cost of this disaster vary tremendously. The NYPRO incident at Flixborough took place at a time when there were few methods prepared for such disasters to take place, and therefore estimating the cost of such an accident is difficult, and many sources vary wildly in their evaluations. It is suggested by the Ministry of the Environment that the overall cost of Flixborough topped $100 million in 1974, equating to over $556 million today, or around £420 million. This comes from the massive damage to the local area, with properties being damaged at over 3 miles away. reaching almost 2,000 buildings in total and resulting in roughly 6,000 public liability claims made against the damage caused by NYPRO. NYPRO's struggle and clean-up. The plant was intended to produce 70,000 tonnes per annum of caprolactam, but was reaching a rate of only 47,000, reaching only 54% of its intended output. Doing so meant that the payback period for the site's equipment was extended significantly, putting NYPRO in a difficult position with poor cash flow. The government put controls on the price of caprolactam, putting further financial pressure on the plant. This, in conjunction with the plant's struggling situation, may have caused additional stress on the managerial staff and contributed towards the incident taking place. Rotarian Jack Gill was president of the local builders' organisation and raised problems of cash flow with which they had to contend during the hectic summer of 1974, and a dilatory approach of the insurance companies, especially during a period of high inflation. As a result, NYPRO provided interest-free loans to builders and persuaded Royal Insurance to meet NYPRO's £1 million public liability insurance claim immediately at a meeting with the British Insurance Association. The explosion gave the world safety lessons it still heeds today, not only in chemical plants but also in other processing industries including oil, gas and pharmaceuticals. NYPRO's response to the situation won over the residents of Flixborough village, its nearest neighbour. In June 1974, the local evening paper carried the banner headline, "Flixborough says never again, NYPRO." By June 1975, that had changed to "Flixborough gives massive yes to NYPRO rebuild." After the disaster. After clean-up operations took place across the affected areas, work began soon after to begin rebuilding the plant. However, the crashing prices of nylon soon became too much for NYPRO, so the losses were cut and the plant was finally demolished in 1981. This again would come at very high costs, with the recommissioning of the plant and the purchase of raw materials, followed shortly by losses in the sale price of their product, and therefore inducing costs of safe decommissioning and demolition of the site. Looking forward. Flixborough has led many management and legislative changes in process safety as the incident exposed many issues that the industry previously had no awareness of. The court inquiry released the Flixborough Disaster Report in 1975. This detailed the severity of the accident as well as the potential causes for its happening and many recommendations to prevent such an event from reoccurring. Management of change. From Flixborough, the most widely recognised development came in the management of change. Before this, changes in a plant were rarely considered as an issue and didn't go through any kind of standardised procedure to ensure their safety and effectiveness. It is because of this that the industry adopted the culture of not allowing modifications to be made without a thorough preliminary analysis. Similar incidents after Flixborough, such as that of the Piper Alpha just 14 years later, further supported such ideas. It is unfortunately the high loss of life at Flixborough which made the need for this precaution clear. It was also made clear that no matter how temporary a building was or how sparsely populated it was, the same design precautions should be taken to the same protocols, standards, and testing used in the initial design of the plant. The failure of the temporary pipe at Flixborough truly signalled the importance of analysis when implementing modifications to a plant. This was unfortunately a very costly lesson for the industry. Prior to Flixborough, there was no structure for making sure chemical plants were operating safely and following all proper standards, even when repairs were made. Flixborough pushed the UK government and others to establish agencies and laws to make sure workplaces were kept safe for their workers. In the UK, the Health and Safety Executive was established, which is now responsible for investigating further disasters and making sure they don't happen in the first place. Shortly after the incident, in late 1974, the Health and Safety at Work Act came into legislation. While many components of the Act had already been finalised before Flixborough, the incident still held great effect in modifications made and additional protections made to ensure the safety of employees in the workplace. Just 2 years later, in 1976, the Seveso Directive came into force in the European Union, as named after a separate incident at the Seveso manufacturing plant in Italy. However, Flixborough held great weight in the legislative process and the guidance given in the directive, with many aspects drawing on the Health and Safety at Work Act. A few years later, in 1982, many of the processes within the legislation around health and safety were streamlined and simplified, as well as covering a wider breadth of work environments and injuries. The aforementioned legislation has since continued to be built upon and is regularly reviewed to this day. Regulation and research. With the incident in Flixborough breaking news across Britain and throughout the world, new regulations had to come into force. The Pressure Systems and Transportable Gas Containers Regulations of 1989 came under the Health and Safety at Work Act as the governing legislation for the design, construction, repair, and modification of pressurized containers. It outlines in detail just what precautions should be made. However, legislators understood that such changes in legislation were drastic, and so there was a period of leeway in which plants could transition from their older practices to those of the newly governed law. And so, within just 20 years after the legislation came into force, every chemical plant in the United Kingdom carried the weight of Flixborough as they all implemented the new legislation in place. As well as the legislative changes that came into effect, the whole chemical industry soon began researching the disaster. It is thanks to this that we may now take for granted the extensive knowledge we have in the understanding of vapor cloud explosions and our capability to model and simulate these accurately. It is thanks in part to this research that we have developed many new designs and technologies to mitigate the damage such leaks and explosions are likely to cause, and we have been able to develop cheap yet strong blast-proof facilities for on-site personnel in chemical plants across the country. In order to provide some standardization for the designs of buildings occupied by staff, the Chemical Industries Association, or CIA, a UK-based organisation, have been publishing a guide since the late 1979s, with its 4th edition now on sale. The Occupied Buildings publication offers guidance on the placement and design of occupied buildings on chemical manufacturing sites, with up-to-date versions continuing to be released to keep up with the progressions in technology and industry best practice. Having such tools on hand ensures that we, as chemical engineers, are better informed in our decision-making when utilising industry heuristics in our designs, thereby ensuring the safety of all those involved. With these changes also came the betterment of engineering techniques with the move over towards using HAZOP studies in engineering. It is the notoriety of Flixborough that caused the managers of other facilities across the country to quickly assess their own plants and question their vulnerability. The industry saw the advantages of the HAZOP study method, and it didn't take long before it became a commonplace work practice, so much so that it is usually taught in universities to their undergraduate students today. However, it is not a set-in-stone system, and it continues to be improved upon as it has been since its conception. With the huge loss of life involved in the explosion, and the potential for further loss still, the chemical engineers everywhere found a new respect for the responsibility they held in maintaining their colleagues' safety. As such, hazard and risk analysis became a core consideration in design implementation, and it became widely accepted that control buildings on site need to be blast-proof. Modules in university became increasingly interdisciplinary, and many core principles of many engineering disciplines are necessary when making safety considerations. Chemical plant design. Before Flixborough, little consideration was given to the design location of administrative buildings. However, there have now been several steps to ensure the safety of staff. It is now recommended that control rooms and admin facilities be placed away from the chemical process. As industry practices are still being refined, we continue to conduct more thorough risk assessments to reduce the risks to the duty of on-site personnel. As mentioned before, control rooms are now designed to be blast-proof or even completely off-site wherever possible, and admin buildings follow this structure of design also. This does pose several new issues for engineers, particularly in ensuring that what we put into the system does in fact happen in the plant. However, new technologies have simplified this task and give more reliable and accurate results as they develop, allowing us to continue improving the safety of carrying out chemical processes in plants. Education. The educational structure engineers go through today is vastly different than that at the time of the cyclohexane explosion at Flixborough. Today, there is much greater emphasis on a diverse education utilising principles from multiple engineering disciplines, and there is a greater respect for process safety in design. This is further emphasised by the IChemE requiring it to be taught in order for a degree course to be recognised and accredited, thereby aiding in the propulsion of an engineer's career towards chartership. Consequently, new charter-level qualifications have come into place in both the IChemE and AIChemE to support engineers in learning how to conduct process safety evaluations effectively.